Okay, so now we're going to see some more details about TensorFlow, specifically how to trace the graph and save it, and also take a look at Tensorboard, which is useful to track the training of the network. So basically, Tensorboard is a utility that you can use during training, log the results as a training, and then use Tensorboard with the browser to see how the training is going, to see those logs. And you can also use the automatic tracing that TensorFlow has to represent the graph of your computation. And I'm going to talk a bit also about the tutorial exercises for this week. Okay, so Tensorboard has these visualization tools. You run Tensorboard and you connect to it with the browser, so it's a HTTP server that you connect to. And when you're training the network, you can write logs with whatever values that you want and track that using Tensorboard. So in your code, it's useful to create a logging directory that is different for each run, because if you mix everything in the same folder, then it's harder to understand things in Tensorboard. It presumes that each run is in a different folder. One trick to do this is to use the datetime module, get a time string for the current hour, minute, and second. So each time you run, you have a different name for the folder, and then you use that as your log folder. Okay, so now we can create a computation graph. If you want to look at the computations, we're going to see this with this example, the logistic regression that we did last week. So we have the weights. It's basically one neuron with the weights and the bias. We have the prediction, which is the sigmoid activation applied to the product of the weights of the neuron and the features, and then added the bias. Then we have the loss function, the logistic loss function that we use to train the model, and we did this by tracing the computations with the gradient tape and then applying the gradients. So if we want to create a graph, we can use the autograph function of TensorFlow that can be used to trace all the computations and compile this into a TensorFlow graph that then can be optimized for execution. So what you can do is to use this decorator here for the TensorFlow function, and this wraps one function that, when executed, is not really executing the computation, but only using the autograph to trace all the computations. So if we create this createGraph function with this decorator, when we call the createGraph function, we are not doing any computations, we are just tracing the graph and creating the computation graph. Now this can have two purposes. One, which I'm not going to show here because it's just a matter of performance, is when you have very complex models, you can do this first and then execute the graph in a TensorFlow session, because if TensorFlow is doing eager computation, going line by line and executing everything, which is what we've been doing so far, it cannot optimize as much the computations. If it has the complete graph first, then it can spread things out in the GPU, CPU, and things like that as it is more useful, and aggregate some computations in a single step, and so on. So if you want things that to maximize the performance, you should use that first, create the graph, and then execute it. But for our purposes here, we are not going to worry too much about that. We are going to use this just to illustrate in Tensorboard how you can see the graph of the computation. So we're going to use this trace on the TensorFlow summary, so for creating this log, and then we're going to create the graph calling that function. You see, so this function is under this decorator. It does not execute the computation, just create the graph, and then we can export this trace to Tensorboard. So basically, by using these steps, we create the graph and we export the representation of the computation graph to the log, which we can then see in Tensorboard how it is. So in this case, I only called the prediction function and exported the graph. So basically, this writer here is this file writer for the Tensorboard. So this TensorFlow summary is the module you can use to add these kinds of things to Tensorboard. I create this writer, and then using this writer, I export the trace of the graph. So this is what you can use the graph for. This is the autograph is implemented in this TF function. We are not going to use this in much detail, but if you want to get some more performance out of TensorFlow, you should look at the documentation. There are some, the reason why we're not doing this is because this way of using TensorFlow is very peculiar about the shapes of the tensors and the types of variables you use. And if you change the shapes of the tensors when you call the function several times after computing the graphs, you end up creating lots of clones of the functions in memory. This can give some problems. So it's a bit trickier to use and not very good for classes where you are experimenting with different things. But if you want to make TensorFlow perform better, look at the documentation and learn how to use this. For our purposes here, we're only, this is only to show you that this exists and to represent the computation graph. So after we run this, we created in our log directory the summary here for this network, for these computations. And now we can run the Tensorboard. We can specify the log folder where we have our different runs, and then open the browser here on 6006. This port looks like Google for Google, so that's the port that Tensorboard uses. And you can then see the computation graph. So since I only called the prediction function here, it only has this graph here stored. So this is what we are seeing here. We have multiplication of the x, and then the y doesn't do anything at this moment. We multiply this with the weights, and then we add everything for the net, and we put in the sigmoid activation and reshape. So this is the prediction of this neuron. If we want to include the loss function too, we just call both of them here. So first the prediction and then computing the loss. And it's the same thing. And now we can see that the y already comes into some place around here for these comparisons. And so it's here. And we have the x here. This is the part where the neuron output is computed. And this is the part where this is compared with the target value, and we compute the loss function. So now we have the trace of the complete graph. And if you have a more complicated graph, then you can trace it also like this. And this can then be used for the actual execution. We're not going to use for that, but you can do this when you create your networks to be able to look at Tensorboard and see if things are as you wanted them to be. So now we can also include everything including the gradients for backpropagation. So remember this function that we created that passed the examples through the neuron to compute the prediction, then the logistic loss, and did this inside the gradient tape to create the graph with all the derivatives. So if we call this one under this TF function declaration to store the computation graph, to trace the computation graph, now you can see the same as previous, but you also have these gradients, the gradients graph here. So this is what the gradient tape generated when it went through all the computations that we did in order to be able to find the derivative of the loss function with respect to the different parameters that we have. You can also add values to Tensorboard. So here we are updating. So this is the training loop that we did before. We have the different batches. We get the gradients, we apply the gradients. And then we do a prediction for the training set. We compute the logistic loss for the whole training set. We had this printout to get a printout of the error, but we can also use the writer, the Tensorboard writer for that directory we created, and write a scalar here. So we can call it train loss. We say which epoch we are in and what the value is. And this basically allows us to plot the graph of the training loss for this run. And we can actually, since Tensorboard is running while you are training the network, you can keep refreshing this and see how the network is training. So for this particular example, it's not very interesting because this is almost instantaneous, but if you have a network that takes hours to train, it's good to be able to look at the graphs while it's learning. Now we can see here that there is a bit of a problem here. So you see a line, and then here there are some loose points because we are getting not a number there, and this happens sometimes. So that NaN means not a number, it means that there was some overflow or something like that in the computations, and we lost the value there. So the reason why this is happening is the logistic loss. We are computing this function by multiplying the class with the logarithm of the prediction, and 1 minus the class and the logarithm of 1 minus the prediction. The prediction is the output of a sigmoid activation function, so something that goes from 0 to 1. And when we are going towards this side, the sigmoid is approaching 0. It's never quite 0, but it's approaching 0. The logarithm of 0 is minus infinity, but we are also doing this multiplication with the y and so on. So actually, the logistic loss should be something like this. But because we are now doing these multiplications with something that is approaching minus infinity and another that is very high and so on, this starts getting a bit tricky numerically, and so eventually it overflows and we have those not enough. So the solution for this is to approximate this function using some tricks. For example, this solution in 2012 is to do this kind of approximation. If we are below 33.3 here, then we are in this linear part and we just output x. If we are within this and minus 18, this is a better approximation and so on. So this prevents that kind of overflow when we are dealing with the logarithm of the sigmoid function and so on. The TensorFlow uses this approximation, but it's the same general idea. But the important message here is that quite often there are these numerical problems, which mean we should not try to do this by hand ourselves, because then things may go wrong, and we can use the functions that TensorFlow has here.
I just want to ask, you explained how to deal with sigmoid function, but isn't sigmoid not used in practice anymore?
No, it's not used in hidden layers, but it's used in the output layers with the logistic loss for binary classification.
Okay.
Okay, so you may have a very deep network, you use rectified linear units, but if you have a binary classifier or a multi-label classifier, for example, then you use sigmoid activations and the logistic loss function. And this is a problem of combining the sigmoid in the logistic loss function, because you have these operations with the logarithms of the sigmoid and you get these strange effects. But this is very used in binary classification or in multi-label classification at the end of the network, not in the hidden layers. Okay, the rectified linear units are for the hidden layers. So what you can do is to use this implementation of TensorFlow, which receives as an argument the logits or the linear output of the neuron. So this is the function here. sigmoid cross entropy with logits. This is a very long name, but it describes what it's doing. So the sigmoid cross entropy is the logistic loss function. And what you get here is just the linear output of the neuron, because now this function will do the whole thing, the sigmoid and the logistic loss in one go, to avoid that kind of overflow problems. So now we need to change a bit the way we implement our network. We have one function for prediction, which includes the sigmoid activation, because when we run an example through the network, we want the probability of belonging to some class. So this is still the same. But now for the logistic loss, we need another part that only gives us the linear part of the neuron without the activation function. So this is basically the same thing, but without the sigmoid there, because this is now what goes into the sigmoid cross entropy function in TensorFlow that does the whole thing, the sigmoid activation and the logistic loss with a different formula to avoid that overflow. So now when we are training, we use this logistic loss function that goes get the logits. When we are doing the prediction, we use the original function. And now we change the training loop too, because here in the logistic loss, to compute the loss for the training set, we call this function, and now things seem to be working. So there are these details that you need to worry about when you're implementing at this level. Next week, I think we'll start with Keras, and then we no longer have to worry too much about this. But still there are other problems that may happen. But you have here the loss functions: mean squared error, sigmoid cross entropy, softmax cross entropy. These two take the logits as arguments, so don't use the softmax and the sigmoid activation before calling these functions, because they optimize the numerical part to avoid those instabilities. This one, by the way, you can implement yourself, because this one has no problems. The mean squared error does not have these problems. But the other two, when you combine sigmoid outputs with logarithms, those can have those instabilities. Okay, so let's see an example that we're going to do this week, which is to predict the fuel consumption of cars. You have, this is derived from this auto miles per gallon data set. I just took some categorical features and so on and cleaned up the data a bit. But what you have is basically the first column, the number of miles per gallon of fuel that the car can do. And the other 7 columns are features like the power of the engine, the year of the model, things like that. So shuffle the data before splitting into training and validation sets. This is always a good idea, because suppose that the table was sorted by year where the car was first built or something like that, then it would, if you would just pick the last few for validation set, it would not be representative of the whole data that you have. Then standardize everything, including the target value if you want. So this is perhaps a bit subjective. Standardizing the features is important, because you should put them all on the same scale and standards. That makes it easier for the network to run. So you can imagine that you're changing the units of measure so that everything has about the same range of values. Standardizing the target value is strictly not that necessary, because if you have a linear output, the neuron can get to where you want. But the problem is that when you have different ranges of values, then things like learning rate behave differently. The mean squared error means a different thing. So if you have a mean squared error of 2 when your target value is in the millions, that is very small. But if you have a mean squared error of 2 when your target value is around 0.5, that is very large. So these things change depending on the scale. If you standardize the target value, you always have things around 0, between -1 and 1, more or less. And so all of these things behave more or less the same. The results are consistent over different problems. The learning rates, you don't have to adjust that much, and so forth. So this is, strictly speaking, optional, but I think is a good idea as a general practice to keep things always in the same range. But remember that in practical applications, you need to store all of these parameters for changing the scale, because if you standardize the features, then for new examples, you need to apply the same rescaling, so the same mean and standard deviation. So you put everything on the same scale that you use for training. And if you are standardizing the output, you need to convert it back into the original units, because what you get is not miles per gallon, but some arbitrary units that you obtain, and you need to convert back to interpret the results. You have 392 examples. Use 300 for training and the rest for validation. In real applications, we should retain a test set so that we can have an unbiased estimate of the true error. For these particular examples, we don't care very much about that, so just use the training and validation to follow, to spot overfitting and follow the training and so on. You have one neuron on the last layer, because you're only trying to predict one value. This should be a linear output. We are not putting constraints on the range of values there. And if we assume that the error is normally distributed on the variable we're trying to predict, the maximum likelihood solution is the mean squared error. That is the function that we need to minimize to get the maximum likelihood set of parameters. Okay? So you can try different activations at the hidden layers, but you'll probably notice that if you use sigmoid, things will bog down quickly. Use rectified linear units, leaky, relu, and so on. You have lots of options in Tensorflow that you can see. Also try different learning parameters, different learning rates, momentum with standard, with stochastic gradient descent. There are other optimizers. I'm going to talk about them in a future lecture, but if you want to try them out now, that's okay too. So this is just to play around a bit with the networks. And what I suggest is that you do this kind of thing, right? You do standardization, compute the standard deviations and the mean, standardize the data, and store the mean and standard deviations so that you can then revert to the original units if you want, or apply the same thing to future examples. You can use this random shuffle to shuffle the data. The random shuffle from NumPy does shuffling in place along the first dimension. So it works for this kind of matrices, and you can do this in a single command, although it's a bit hard to interpret if you don't know exactly how it works, because it seems strange that you're shuffling the whole matrix. It only shuffles in the first dimension. If this is confusing, you can use the other more wordy version that I showed previously, which you create an index, you shuffle the index, and then you pick the rows according to that index. So that is easier to understand, but this one is faster to use. Just don't make the mistake of putting data equals to shuffle, because this one doesn't return anything, and then you get a none on the object and it won't work, okay? This one shuffles in place. Now, one thing that you can do to create the model, instead of using that method we used of using the global variables and creating those by hand, we can create a layer function that receives the inputs into this layer and how many neurons we want. So the shape of the weights will be the number of rows that we have is the number of features that we will have in the input. So it's the number of columns in the input matrix, and that is what we have here. And the number of columns in the weights matrix is the number of neurons. So this creates a variable, a tensor, with the weights of our neurons. And this creates the biases for our neurons and returns both variables. And now we can create a network that receives a matrix of features, X, and has this list with the number of neurons per layer. So basically we start with the previous layer as being the input data, the X, and now we follow through all of these layers, and we create a new layer using the previous matrix and the number of neurons indicated in this list. And now we point the previous matrix to the weights of the following one, so that we know how many neurons we're going to have for the next layer. And basically, looping here, we create all the variables needed for the layers. Now, there is one trick here. When we are creating the network to do the predictions, it's useful to have the weights and the bias as tuples, so that then we can unpack and do the computations. But when we give this to the gradient tape, it needs to have all the variables in a list. So you cannot have lists of tuples or lists of lists. That will be confusing for gradient tape. So this one is appending a tuple. This one is extending the tuple, so that we create a single flat list with everything in the same order for the variables. Okay, but this is just a trick for that. And so now we can create a representation of the network, which is this list of tuples for the computation, and also the list with all the variables we need to feed into the gradient tape. And this should be the example of a network: 25 neurons, then 15, then 1. And the number of parameters in the neurons starts by looking at the number of columns on X, and then by looking at the number of neurons on each previous layer to determine how many weights we need for the following layer. So now prediction is simply starting with the data, the features. We are doing the matrix multiplication with the weights, adding the bias, and then adding an activation function. So in this case, for all layers except the last one, we add a leaky ReLU with the standard, with the default parameters. I think it's 0.2 or 0.3 of leakage. And then we do the same thing for the final layer, but we don't add an activation function in the final layer, because this is a regression and we just want the final one to be a linear neuron. So now you can create the graph here, the same thing that we did before, write the graph to Tensorboard, so you can see all the different multiplications of the weights, additions, and so forth. So this is a bit ugly, especially if you have a large network. So what you can do is, when you are creating these computations, you can use this name scope from Tensorflow and group together several of these computations into the same name. So for example, we can call it layer and give it the number of the layer. And if you do this, now the computation graph is much prettier, because this is the first layer, the second layer, and so on. And you can click one of those if you want to see exactly what is inside. But when using the name scope, you can create these prettier graphs by grouping together the details of the computation. Okay, so now you can try, for example, the SGD optimizer with a small learning rate and a large momentum. Batch size of 32, but you can experiment with this. So remember the squared error loss function. I didn't show that part, but you should be able to do that. If you have many neurons, you'll have this not a number again. The problem here now is in weight initialization. So if you have many neurons, then you have a large number of values that are added together for the next layer and so on. And if the weights of the neurons are not very small, these things can add up to very large numbers, and you have, again, overflow problems with the computations. So one way of doing this is scaling the initialization, depending on the number of neurons you have coming in, going out. There are different formulas which we are going to see next week. But for now, one quick trick is just divide by the number of neurons the standard deviation, on the random normal that initializes the weights. So this makes the weights smaller if you have a very large layer, and it reduces the probability of these things occurring. Okay? But this is just to show some problems that we have when we go from the theory, where in theory this would never happen. In practice it happens a lot because we are dealing with finite representations of these numbers. Okay, so now at the end we have an error value, which is the mean squared error, or the mean of the square of the difference between the prediction and the target value. So if you take the square root of that, you get the square root of the mean squared error, which is something that is in the same units as the prediction and the target. And if you multiply by this parameter that we have here, so remember that when we did standardization, we stored the standard deviation of each column in our data, and the first column is the target value of the miles per gallon. So we divided this by the standard deviation to standardize. If we now take the square root of the mean squared error and multiply by that standard deviation, we convert everything into miles per gallon. So this is a good way of looking at the error in miles per gallon without forcing the network to go into very large numbers for the prediction, which could affect the learning rate you can use, the gradients, and so on. Okay? So try different architectures, monitor, train, and validation with Tensorboard. So this is basically to experiment with these things until you understand how they work. Another exercise is to use softmax for multi-class classification. So last week we did binary classification with a simple logistic regression. Now here we do a regression problem and a multi-class classification. We're going to use the NIST data set. So this is the data set of handwritten digits. These are images of 28 by 28 pixels, grayscale, with the handwritten digits that you can get directly from cache. So when you do this load data on the NIST object there, it will download the data to a cache the first time you use it, but afterwards you already have it on your computer, so it will be it will load instantaneously. And it gives you, I think it's 60,000 images for training and 10,000 for testing. It separates them. These are the labels and the images. We're going to reshape, I'm not sure what shape they are in, but we are going to make sure that they are in a flattened shape. So each row is one image, but each image is a vector with all the pixel values and not a matrix, so that you can feed into your dense layer. So we're going to reshape into this 784 features for each image. We're going to use on the training set 50,000 for training and 10,000 for validation. And you can use the same kind of functions that we did for the miles per gallon problem. The difference now is, remember to use the softmax cross entropy with log x for the loss function. And for the prediction, you put the softmax activation function. But for the loss function, don't put the softmax and use this one, otherwise you'll have problems with numerical stability. So the same thing that we saw previously. One other thing that you need to do is to convert these labels. These labels are integers, so this would be 0, 1, 2, and so on. These are the class labels. But in softmax, you're going to create an output layer with 10 neurons, and you get 10 values with the distribution of the probability of the image being in each class. So to train, you need also the same representation of 10 values, where you have zeros in all the classes the image does not belong to, and the 1 on the class the image belongs to. So this is called one hot encoding, and it looks like something like this. Well, this image belongs to this class here, this second image belongs to this class, and so forth. Because this is what your network must approximate when it's trying to predict the class for these images. You can obtain this easily using this utility function, toCategorical, where you put in the labels, which are integers, and the function counts how many different labels you have and gives you the one hot encoded version. Okay? If you want to measure accuracy yourself, if you want to convert from something like this in the output of your network to an integer with the class label, you can use argmax from NumPy, because this tells you the index where you have the maximum value, and that will give you the class label. Okay, so this is what you're going to do. Compare different activation functions in the hidden layer, try different network dimensions, and check for overfitting and so on. So basically, you're going to create a network that inputs the images as vectors of pixel values and outputs the probability distribution of the 10 classes here. It's important to remember that for prediction, you want the softmax activation, but for the loss function, you want to put directly the linear part of those neurons into the softmax cross-entropy function to avoid those problems with numerical instability. Okay, you can see more about this data set here if you want. This is an historical data set for machine learning and so on. It's used for a long time now. Note that the output of your network will be a vector for each example. So if you put a batch of examples, it's going to be a matrix with 10 columns, each row for each example, and what the columns represent are the probabilities of belonging to each of the 10 classes. So what we saw today was this, how to use Tensorboard, how to use the autograph function of Tensorflow to get the graph. Eventually, you can try to run this in graph mode, but we are not going to do that here in this course, because if you use scatters and so on, all of these optimizations are already taken care of for most practical purposes. And the graph mode raises some additional details and difficulties that we prefer to avoid in the tutorials. There are these problems of numerical stability that you have to take into account. They can occur if your weights are too large, if the learning rate is too large, if you don't use the appropriate version of the loss functions and so on. And we saw these exercises that you're going to do. So last week you did binary classification. You had these exercises with the GeneDeck, with the sigmoid neuron. Last week we used other data sets, but this network you already created. This week we can focus on these other types of problems, regression and multi-class classification.